So back to the lecture. So we started talking about transference at the end of last lecture. So just to recap at a very high level, transference is all about some modality that you care about. All right, back to transference. So in transference, you care about learning in some modality, but that modality might have limited data, limited labels, noisy labels, and so on. And the whole goal is to use some other modality in which you have more data to help you learn that modality that you care about. So the first sub-challenge is about transfer learning. You care about learning in this modality. Without that much data, you can use bigger pre-trained models, train larger amounts of data to help you. The second challenge we're going to talk about is co-learning. If you have a task that you care about, can you use some other modality as extra input or extra output to help you learn? That's it. And also going to talk about model induction, where you care about learning in one modality, you have another better trained classifier. Can you share some information between these two classifiers to help you learn? So first of all, for transfer, we actually talked about transfer quite a bit, right? You have a big model like BERT. Ideally, it's pre-trained, you don't want to change this too much. You want to use some of the knowledge to help you learn in your modality A, which is less data, but learning a combined representation. And we saw some examples of this, just to quickly recap. If you have a language model or a BERT model, sentence encoder, you can very quickly adapt images through an encoder and just learn the adaptive parameters while keeping the rest of the model frozen. And you can do this multiple times to eventually get a representation that both contains your adapted information from the task that you want to condition or that you care about, and also the pre-trained information from your frozen parameters. You get a best of both. And as a result, you can very quickly do things like question answering based on, for example, new images or new vocabularies that you want the model to condition on. We just saw an example of representation tuning. You can take a pre-trained model, open up its parameters, encode some other conditioning information. So if this is language, think this is your audio and visual if you want to do video classification. And we know that your pre-trained model is going to primarily do really well, right? That's the one trained on lots of data. So instead of changing all the representation, just learn a shift to minor change, to change your representation in a small way based on your audio and visual information. And that gives you some final representation, which you can then use for classification. And the intuition here is that this dot is what you have beginning at the language model, and you're going to shift it in your representation space with some positive audio video or some negative audio video information if you want to do like video classification. So that was more opening up the representation and transferring information from your pre-trained model via the representation. A specific example they used this for was to do video sentiment analysis, whether it's positive or negative. So language already contains some information. That's the dot in the middle. You can classify that as positive or negative. You also want to use audio and video information, whether a person is smiling or laughing to do classification, right? So you can shift it, it's positive, predict more positive. You shift it, if audio video is negative, to predict more negative. And we just saw a lot of examples. So like this transfer by pre-trained model straddles generation and also transference, because a lot of the pre-trained models that we have nowadays are generative based or masking based. So we saw how you can do this entanglement, right? By imposing a KL divergence on your latent variables, that makes the latent variables more understandable and more controllable. We saw conditioning. If you have a big pre-trained model P of X, like your language model, diffusion model, and so on, you can also have, using paired data, learn a conditional model P of X given Y. Right? Prompt tuning and representation tuning was what we saw just now. You can also do classifier gradient tuning or classifier free tuning. All these that straddle both generation and transfer with pre-trained models. And we should start talking a little bit about multitask and transfer learning. So instead of just transferring from one pre-trained model, you can also try to train a model across many different modality subsets, each defined on their own separate tasks. And the big benefit of this is that if some of these tasks are low resource that you really care about, you either don't observe that many modalities or don't currently obtain that many labels in that task, you can hopefully use the shared either input information or output information to other tasks to help you. And we saw one specific implementation of this, where if you had a bunch of modalities, each observed for a subset across your tasks, you can first standardize your input sequence. You want to make sure all the inputs are a similar format. Language would be a sequence of words, video a sequence of frames, audio a sequence of timestamps, and so on. Append a modality-specific embedding that identifies that the video is common across these three tasks. And then you can start defining, at least what we found is that you can define a generic model, a multimodal transformer model that could learn generic representations And with a task-specific classifier, could classify many different tasks at the same time. Right? So you could classify videos from language, video, and audio. You can classify sentiment and emotions from audio and video. You can classify robot dynamics, or how the robot should be manipulated given what the robot sees in video and what the robot feels in touch sensors. So that's time series. And a really cool thing about this line of work, which other people are also quite working on, is that you can train the same model architecture. So the model is fixed, and more so the parameters are also the same. Right? The same model is repeatedly applied to video and time series fusion, or audio video fusion, or language video audio fusion to do prediction across different tasks. Right, any questions about this approach? There are quite a few questions at the end of last lecture. Right, so how does this work? Let's go a bit more detail. So let's say these are all your tasks. What you can first do is you can train separate models for everything. Separate models. You can take the best model for sarcasm, best model for robotics, best model for multimedia, image text retrieval. You can train all these separate models denoted in different colors. And over here, we're showing a plot basically of how efficient your model is, adding up all the parameters. You have separate models, you can add up all the separate parameters, and also help with the performances on average across all of these tasks after some normalization. So all these blue dots are all model combinations, different assortments of like the best 5 humor models, the best 5 robotics models, now multiplied and composed with each other. That gives you a lot of points. You can draw the Pareto front. Those are points which achieve either good performance or good efficiency and are not dominated by some other point which is better in both performance and efficiency. You can then train a standard multimodal transformer. So the good thing about this is that you're still standardizing the architectures, so the colors are all the same. It's that you're training them separately. So you have a set of single task training where the parameters end up to be different. That gets you pretty good performance. You're quite efficient because the transformer implementation is quite different as compared to some of the other models. And performance-wise, you're also achieving relatively good performance with respect to all the other models. But the coolest thing is if you start training a single model for everything, right? Same architecture and also same parameters, train in a multitask manner for everything, you're roughly maintaining performance, which is good, but you're also cutting down the number of parameters you use, essentially reducing the number of unique parameters by the number of tasks that you're doing multitask over. So in our experiments, that was about 4 to 6. And finally, you might think, it seems naive, like using all separate models for everything is naive. It might be overfitting to your tasks, to your architectures. Using the same model for everything is also kind of naive because how do you know whether I should use the same model to both set data versus video data and sensor data? So ideally, what you should be doing, which is what we found in subsequent work, is you should do something in the middle. You should have a model that is largely the same, but unique parameters tailored to specific data sets. If you know that those modalities or those tasks are different, right? We call this heterogeneity aware sharing. And how do you determine which modalities are similar and which modalities are different? That's in general a very difficult question. We're going to get into a little bit of it in quantification, because as you recall, quantification, the last challenge, is all about better understanding the data and the models and multimodal learning. So ideally, if you could solve the problem of how to determine whether a pair of modalities are the same and should be encoded by the same model, or different and should be encoded by different models, then you can get ideally the best trade-off between both parameter saving, efficiency, and performance. Right? And at least our initial attempts, we did find that you can actually get better performance than those which naively share everything, while also having a trade-off, right? The more you separate things up, the more closer you reach best performance, but use more parameters. So you have this curve that Pareto dominates over current methods. So that was on the multitasking part. You can train a model in a multitask manner across many different modalities and tasks. We also found a cool thing where you can also do transfer learning. So if you learn a model on, for example, this subset of modalities across a couple of tasks, you can then transfer it to some other set of modalities and tasks, right? And the cool thing is that some of these modalities that you transfer it to should overlap, but some can also not have overlap. So if it doesn't overlap, you're just basically fine-tuning just an embedding dimension for this new modality, for example, tables. And we can see some really cool results, right? Depending on how many source tasks you pre-train before you start transferring to this new task. If you don't pre-train on any, that's just supervised learning on this new task. Mimic is some healthcare prediction based on time series and tables. If you transfer on one task, if you pre-train on one task before transferring it over, you start seeing some boost in performance. And if you pre-train on two tasks and transfer it over on three tasks, you start seeing more and more performance boosts. Likewise, for this other data set on humor prediction, right? You can just do supervised learning directly, that's about 63%. But if you transfer based on pre-training on one or two tasks, you can slowly and get better. And just to point out some of the works that have also done this, DMind had work on Gato. They're primarily robotics and reinforcement learning based, but the idea was also very similar, right? You have text, you want to do text classification. You have image and text, you want to do question answering. You have all these image, proprioception, action, which are your reinforcement learning settings. Just standardize all of them as a sequence, right? Text is a sequence of words, image is a sequence of frames, your reinforcement learning settings are a sequence of state action rewards, and so on. And what you can do is also append a specific embedding to tell you that this is, for example, the action modality, this is the image modality repeated across these three tasks, and that's the language modality. Train a standard model, so in this case also something like a transformer model, and you can get it working for different tasks in a multitask manner. So again, similar findings, same model architecture and same parameters. You can do reasonably well. You're not going to get state of the art in any of these tasks. That belongs to the task-specific method, but you're going to get reasonably good performance with the same model. Yes?
Can you please talk in brief about what this model is about?
Gato, so you can look at a paper, but Gato essentially is a transformer. There's nothing special. The transformer that after you standardize the input sequence, learn an autoregressive model that takes in, for example, I'm going to London, and then completion for business. It takes in the image and the question, the image of the cat, what's in the picture, and complete, it's a cute cat. You take in a sequence of state action reward transitions. In reinforcement learning, you encode the first part and you try to predict the next actions given the next states. So Gato is nothing fancy either. So it's autoregressive transformer model. Okay, so you might think, oh, this is good, right? Why did we talk about multimodal for 3 months? Only to say that you don't have to care about the modalities, you don't have to care about the tasks, just slap on a big model. And of course, there's a lot of open challenges here, and there's a lot of implicit assumptions that these papers are making. So you want to think about what these assumptions are when you read these papers. So the first big assumption is that all modalities can be represented as sequences without losing information. You can do this standardizing of sequences. And of course, this makes sense even for the ones that seem to make sense, like language, video, audio. Just by sequencing them, you're losing a lot of information on the implicit structure along these modalities, right? And then when you go to settings where you can't really standardize, sequentialize them, if you have like continuous data, if you have high dimensional data, you might not even be able to represent them as discrete sequence elements. Right? So that's the first assumption you're making. You're not going to lose any information when you standardize everything as simple sequences. The second big assumption you're making is that all the different heterogeneity in your modalities can just be captured using these modality-specific embeddings. Again, no one knows whether that works or doesn't. My hypothesis is that this is not the most efficient way to do it. But the assumption made by all of these is that the only difference in video and time series, after you serialize them, is the fact that you have a different embedding than before. Okay. So all the heterogeneity can be summarized in these embeddings. The third big assumption is that all of the cross-modal interactions, cross-modal interconnections, can be captured using the same model. Right? So in this case, it was a cross-modal transformer model that can capture the interaction between video and time series, the interaction between audio and video, the interaction between language and video, video and audio, and so on. That's a big assumption. It seems to work in practice, but that only seems to work because we have big models, a large amount of data, which allows us to approximate almost any type of interconnection, but it probably will not work on small data sets. Right? So that's another big assumption. And just on the side of multitasking transfer learning, there's many other dimensions. Here are some of the notable works, which I put names on. This works on applying a single encoder for different modalities. Now, we started at the beginning of the course talking about how you want to respect the structure of each modality. Vision seems to be more suitable for convolutional network, for vision transformers. Language seems to be more suitable for LSTMs, RNNs, or transformers. But recently, there has been some convergence to the general transformer architecture. Again, whether that's the best or what assumptions that these models are implicitly making, they may or may not be the best choice for your class. That's unifying the encoder for unimodal learning. There's also some other work on, in general, multimodal multitask learning. A lot of that in language and vision space. You pre-train a model across many different tasks, like VQA, VCR, all of them based on images and questions. And you can get a reasonable model that multitasks over all of them at the same time. And the ones that we just presented, HiMMT and Gato, those just kind of expanded the number of modalities that these models could support. So a lot of open challenges. How do you get it working for actually low resource? Right? A lot of the multitasking pre-training assumes that you have a good amount of data for each one. How do you actually get it working for truly low resource? How do you get it working for beyond language and vision? Those have been quite studied a lot. When you go to other modalities, for example, high dimensional ones or high frequency ones, it might not even be clear how to segment your data into a sequence. So a lot of these current methods aren't going to work. How do you get it working for modalities where your state-of-the-art unimodal encoders are not based on deep learning? Tabular data is an example where deep learning doesn't achieve state-of-the-art. So you can't just serialize it as a sequence of table entries and put it into a transformer. Ideally, you want to do something more different. And of course, all of these, you're making fewer assumptions on how to design the models, but you're going to pay because you have more complexity in data, modeling, and training. And finally, most of these are black box models, right? So quantification will go deeper into how to interpret these models. Okay, any question about transfer via big pre-trained models or multitasking transfer learning so far? Cool. In the next section, we're going to talk about co-learning. So in co-learning, as we've motivated, you have some modality that you care about. There's very little data in that modality. Can I use some other modality be not in the form of pre-trained models or representations, but just the data? Right? How can I use that data as an extra input during training, either at the input level or at the output level, to learn a better representation between both modalities A and B? So here's an example. Here's a very nice example I liked back in 2013. So let's say you want to do image classification. You have a bunch of images. Some images represent cars. Some images represent dogs. Some images represent horses, right? And if you just try to do image classification, you have some labels for cars, dogs, and horses, and you could predict these three categories, right? But what if you also want to predict the category of truck or a different category like a cat? And you don't have images for them. What can you do? You don't have label images for them. What can you do? So what this paper found was that you can learn a coordinated representation space using both images into image embeddings and words into word embeddings. So here what this figure is showing is that all these centers, auto, horse, and dog, are word embedding points in your space. And all these nearby clusters are image embeddings that have been projected by coordination into word embedding space. So all the images of cars get into all these plus points that are centered around auto. All these images of horses become these diamonds centered around horse. And all these images of dogs become these triangles centered around the word dog. And you can do this using any representation coordination method, right? So these folks back in the days used like a max margin loss, given some paired images and word embeddings. So the really good thing about this is that you have a lot of word embedding information. And we all know that word embeddings contain some semantic structure in the representation space. They, for example, encode the fact that truck is close to auto and very far away from cats and dogs. Cat should be close to dog because they're all animals, and also close to horses, but relatively close to the dogs because cats and dogs appear more in that context. Right? So what you can quickly do is that if you have a new image from unknown class, let's say this is a cat image, and you learn the image encoder. Normally, if you just learn the image encoder without word embeddings, it's going to be very, very difficult for you to predict cats. But if you coordinated your image embedding space and your word embedding space, and you're going to project it encoded image representation space that is actually close to the word embedding space for cat. And you already know what the word embedding for cat is because of the word embeddings that have the semantic structure in your space. they actually find that you can do very quick zero-shot classification of new image concepts by projecting them into word embedding space and leveraging the fact that you know where these word embeddings are in word embedding space. So, an example of co-learning, right? You had some modality which you care about, image classification. You don't have that much data, you don't have any labels. For example, you don't get the label for cat images, you don't get a label for truck images, but you can leverage your geometry of word embeddings as an external input, do representation coordination, and eventually end up with a model that can very quickly classify these cat images and truck images. Okay. So that was co-learning via representation coordination. We also found that you can also do co-learning by representation fusion. So here's the setup. So let's say during training, I have two modalities, and I'm learning a fused representation, which I then use for prediction. Right? So I have multimodal data to this. For this, you have pairs of XA and XB. And I'm also going to train a multimodal fusion model. At test time, let's just say I have modality B at all. I only use modality A. And I fill in modality B with 0 because I don't have it. So technically at test time, this is a unimodal classifier, right? Because you're only taking in data from modality A and not using any data from modality B. But you're still putting it through whatever fusion model, except the modality B has been filled with zeros. And compared to this setting, which is just unimodal learning, I train during training with modality A, unimodal classifier, and I test at test time also using modality A, unimodal classifier. So you can see that at test time, both are consistent, right? At test time, both tasks only use modality A. But it's just that one of the models has been trained with a multimodal fusion model, and the other modality putting in zeros. And the other setting, you just train this unimodal model from training to begin with. And we actually find quite consistently that this setting, training multimodal and testing unimodal works better than training unimodal and testing unimodal. So again, you see this phenomena, right? You see this dotted line phenomena where this other modality B was introduced during training to learn a common representation, a fused representation, but B is not given during testing. And for fair comparison, you only have A during testing in both settings. And the one that you have introduced B during training allows you to learn a better classifier for A. So a specific example, the specific setting that we're using this is that at testing, we care about language-based sentiment analysis. So just given text, can I predict positive or negative? So you can just train a language-only model and do language-based sentiment analysis. But what we found was that you train a video-level sentiment analysis classifier, so with language and video and audio happening at the same time. And when you test it on language-based sentiment analysis, just put zeros for audio and video. Those are modalities. And you end up having a better language-based sentiment classifier than one that was just trained on language only. Why this works? We don't know. We don't have a theory for why this works. This seems to work empirically. We have some intuitions that I'll get into in a bit. But open question why this works in exact theory. Okay. So before you actually train a unimodal classifier and multimodal classifier, just for embeddings. We had, at least back when we wrote this, 2018, we found that this was, you could just use word embeddings for language, and you're consistent. So word embeddings would be here, and auto embeddings, XA would also be word embeddings, and XD were like facial gestures or acoustic features. And we did quite a lot of experiments, although and based on the experiments, it seemed to be robust to which embedding you started with, and also which specific fusion model or unimodal model they started with, right? Whether it was like a tensor-based fusion or early-based fusion or LSTMs, RNNs on the classifier side. So it seemed to be pretty robust. But yeah, I mean, without exhaustively testing all possible embeddings, I can't answer that question for sure. But they seem to be pretty robust. So that was more co-learning where the additional modality was added at the input level. There's also some cool results showing that if you add the other modality at the output level, you can also train an enriched modality by predicting the other modality as output. But you're still leveraging modality from both A and B. So there's two examples of how this can work in practice. Okay, so there's two examples of how this can work in practice. So normally, this is how you learn representation. Right? You have two modalities, language and video, for example. You use both as inputs. You learn a common representation with both as input and use that for prediction. But the biggest issue here is that you always need both modalities at test time. So you always can be sensitive if either one of the modalities is missing. And in code learning variety generation, our insight was that instead of learning from both modalities as input, can you learn via translation? Can you take a language, learn a representation, and use that representation to predict the other modality, right? You're still using information as both, from both modalities. Your insight is that you want to use the vision modality as a prediction target to force you to learn everything there is about language that is most relevant to vision, right? Learn the common information between language and vision. And once you've done that, you can use this representation to predict the targets. So during test time, what happens is that you take in language into this common representation, and this encoder has been trained with the objective of creating these images during training. You learn a representation that is still going to be a joint representation between language and vision, and then you can use that to predict your label. And the best thing this now is that you're using both modalities during training, but at test time, you're just using language, right? You're going to be robust to any imperfections in the vision because you're just using language as the input. So this initial attempt worked well sometimes, but it wasn't perfect. One big issue we found was that when you start learning this translation, you have this multitask prediction head, right? You have to learn this representation that can predict the images and the videos at the same time, and you also want this representation to predict the label at the same time. So in such a case where it's super dominated, where one is much easier to predict than the other, sometimes the model just ignores the prediction of the visual modality and just completely does language only prediction. So one trick that we found to really get this working was to do two-way translations. You start with language, you learn the embedding, use the embedding to predict vision, and whatever you predicted in the vision, you try to recreate the embedding and recreate language. So kind of like cyclic translation, cyclogen. We're trying to force the model to learn as much as you can about predicting the vision so that the vision can also recreate the language. Right? If you've learned the joint information about language and vision successfully, you should be able to use language to predict vision and use that joint information to recreate maximally what you could about language, at least for the joint part. And you do better optimization, you train it better, but you still retain the benefit, right? You use both modalities during training, but in testing, all you need to do is to take language, go into representation space, and predict the labels. Right? Only language is required during training. You're going to be completely robust to any imperfections or noise in the vision modality because you don't have to take it in. So that's exactly this figure, right? You have a modality that you care about predicting. You can use the other modality, vision, as an extra target during training to encourage the model to predict that and learn a better joint representation. And this seems to work better than a lot of language-only methods that don't use the prediction of the other modality. And also works a lot better than even multimodal methods, where both modalities are taken in at the input level. And subsequently, people also scale this up. People show that normally we train on a language model. You just use text, right? You take some sentence, you mask out some parts, you recreate the masked portions. You can also start fine-tuning these language models by also predicting images that co-occur with text, right? So when you're encoding humans into the word humans into language model space, also predict these visual tokens of humans. If you're encoding language and speaking, not only you do the mask prediction of the missing words, you also predict the visual tokens. So that's also like this, right? During training, you're further training this language model with visual tokens as the additional output. But once you're done with that, you just apply it, and test it, you're still just using language, right? You don't need any more visual tokens, images. So that's also co-learning. And as the student rightly pointed out, what are the big assumptions in both this, or all this co-learning, where only one modality is present during training and not present during testing? The big assumption is that what you're going to capture is the middle, right? Obviously, if you don't use the second modality during testing, you can't possibly have information over here. So any visual specific information like the background, like the texture, depth, motion, they're going to be discarded. All you're going to do is to encourage the model to learn the intersection as much as possible, which the information contained in both modalities. So that's good. That's perfect. If your label is actually contained within this. And in many multimodal data sets, the label is contained within the intersection. But if your label touches, for example, vision-only information, then you're going to suffer. Like that part you just can't capture at all. Okay. So for example, the core learning via generation basically takes in language and tries to predict as much of a visual as possible. It basically biasing a model to learn this thing. And it works on co-learning via both as input. You're also using both. You're discarding vision at test time, but you're encouraging the model to learn as much about the intersection as possible. Okay, any questions about co-learning so far? Great. So in the last part, we're going to talk about model induction. Model induction, the biggest difference is that I'm going to try to keep my models separate. Sometimes I don't want to fuse or learn models at the same time. Can we keep our models separate while also inducing common information between them through co-learning? So again, a lot of the assumptions, as I talked about earlier, a lot of the assumptions is that the task that you have defined, your label Y, lies in the intersection of both modalities. Y is basically the information captured in both modalities. In a lot of these co-learning in this model induction methods, if you have label Y touching the unique parts, you're not really going to be able to capture that using these methods. So to formalize that, at least which is going to be really useful for this next algorithm we're going to look at, we're going to define this multi-view redundancy assumption. And this basically comes from the co-training paper, a really early paper on multi-view learning. This multi-view redundancy assumption is essentially how to formalize the fact that your Y label only occurs in the intersection. So more formally, you can look at it as your two views, x1 and x2, and x1 and x2 should be conditionally independent given the label. Conditionally independent given the label. Equivalently, what that means is that if two things, x1 and x2 are independent, they have zero mutual information. But this is conditional independence, so it's going to be conditional mutual information. So the mutual information between x1 and x2, conditional y is 0. So what does that mean visually? So if this Venn diagram shows my information theory metrics, right? So the circle for language is the entropy of language. The circle for vision is entropy of vision. The mutual information between x1 and x2 is just this intersecting part, right? The part where they overlap. Conditioning on y in any of these information theory metrics basically means observing it, and therefore we reduce the information about it. So conditioning on y means removing y. So you subtract the circle for y, and that should be 0. So what that basically means in practice is that was the mutual information between x1 and x2. That is also the information, the entropy of y, and the mutual information between x1 and x2 conditional y is basically 0, right? Y explains all the difference between x1 and x2. So there are some key implications of this, and you'll see this when we start talking about the algorithm. The first big thing is that Y explains all the difference in x1 and x2, right? That's as we mentioned. The only different thing between x1 and x2 is what I want to predict. The other big thing based on this visualization is that you can use language. You can predict Y perfectly. You can also use vision. You can also predict Y perfectly, right? If my Y was any other part, if my Y was, for example, a circle like this, that straddles the intersection and straddles something within language and straddles somewhere in vision, say somewhere like this, then the information between x1 and x2 conditional y will not be 0. It will be the part between x1 and x2 which you can't use to predict y. But that's the multi-view redundancy assumption. I'll get into this in a bit more. But just talk about the example that they use that claims to satisfy this multi-view redundancy assumption. Again, that was a co-training paper back in 1998. X1, let's say you have a bunch of web pages, right? And you want to classify these web pages into a category. Is it academic? Is it sports? Is it news? Is it music? X1 is the first view of the web page. That's the text on the web page itself, right? What the web page starts talking about. X2 are the text on hyperlinks that point into your web page. Right? If any other web page references this web page, the text on those web pages. So in this case, you can kind of see, right? The only difference between the text on the web page itself and a text on the hyperlinks pointing into the web page, the only difference is the actual category of the web page. That explains all the difference between these two views. And at the same time, if you have text on a web page, you can probably predict the category. If you have hyperlinks pointing into the web page, you can also probably predict the category, right? So either view is sufficient and agree on predicting the label. So the code training algorithm works like this, right? I'm going to assume that you have some label data, x1, x2, and y. So that's the text on the web page, the links pointing into it, and the label for what it actually was. And you also have some unlabeled data, x1 and x2, right, without labels. We're going to start by training two separate classifiers, as we've motivated in model induction. I'm going to train the first classifier, f1, to just predict based on view 1, right? Specifically, I'm going to take all my data, I'm going to disregard x2. I'm just going to look at x1, what that says, what the text is, and try to predict my label on the category. And I'm going to train a separate classifier, f2. I'm just going to look at the second view, which is the text coming in from the hyperlinks, and try to predict the label. Now, the key idea here is to use these classifiers to relabel my data, because I have a bunch of unlabeled data. So what I'm going to do is to take classifier f1 and to label some confident examples in my unlabeled set, right? So I'm going to take the unlabeled set x1 and x2 and label it. So set the y as whatever my function classifier predicts on the x1 view of that data. Right? So using classifier f1 to label more data. Then I'm also going to use classifier f2 to label more data. Take in unlabeled data x1 and x2, apply my current classifier f2 on a second view to get new labels. So you're slowly expanding the label data that you have. Although you're not getting ground truth labels, you're getting pseudo labels from where your classifier currently is. Yes.
So, how do f2 is trained on the label data or unlabeled data?
F1 and F2 are both initially trained on the label data. So you start with something. We have very little limited data, right? F1 and F2 are not going to be very good at the beginning. But as we will show, even though they're not very good at the beginning, by using that labels, the pseudo labels from these weak classifiers, you can actually still start improving your classifier iteratively. Okay. So you have initial classifiers, you use them to label data, F1 on the first view, F2 on the second view. You have a new bunch of new labeled examples, and you're going to repeat. You're going to put these new labeled examples back to initially reiterate and train your F1 and F2 and repeat until there's no more labeled examples. And when you're testing, given a new unlabeled sample x1 and x2, just ensemble or combine F1 of x1 and F2 of x2. Given it two new separate classifiers that you've trained. So this seems kind of complicated, but let's warm up by analyzing a single view setting. Right? In the single view setting, it's much easier. You just label data x1 and y, you have unlabeled data x1. Right? You're going to do something very similar. You start by training a classifier on x1 to y, that's f1. You start by labeling your data, taking some very confident examples in x1, putting the pseudo labels as f1 of x1. Whatever the weak classifier I have tells me a label should be. I'm going to treat it as a real label, put it into my label data set. I'm going to repeat to train the classifier with my new expanded set of labels, and then keep using a new classifier to label more unlabeled data, and repeat until I have no more unlabeled samples. Right. So during testing, given this unlabeled sample x1, just output your classifier on x1. Right. This is a single view setting of co-training. They call this self-training. So to see this in practice, let's just say you have these points. Again, a single view, a single modality, that's everything. The student's question was that the example that we gave on x1 being the text on your web page and x2 being the text hyperlinks into the web page, we can very clearly see that both are roughly text, and the only difference is the category in the web page, right? That explains all the difference. So that's why we drew the assumption that in one circle and the other circle, the label was exactly contained in the intersection. What if you have like more complex modalities and more complex labels? An open question on two regards. First of all, how do you quantify the intersection between modalities? That Venn diagram is an open question. Very difficult for high-dimensional spaces. You can't really estimate information theory in high-dimensional spaces. Second of all, how do you quantify where the label is with respect to the intersection? Also open question. And third, more importantly, can we relax some of these assumptions? So you either match your data closer to the assumptions, or you relax your assumptions so that it reflects better real data, right? So there's also work on kind of relaxing some of these assumptions so that the label doesn't have to be exactly in the intersection. But yeah, great question. So yeah, just to show this single view version of code training, which we call self-training. One modality, triangles. Red shows the ones that have been labeled as the first category. Blue means the ones that have already been labeled as the second category. All right. Start by training a classifier. That was the first step, training just a classifier. And then what you're going to do is that, let's say you have a new set of unlabeled samples coming in. Like you have some unlabeled triangles which are close to red and some unlabeled triangles which are close to blue. So you can already start seeing that among the unlabeled samples, some are very clear, right? You should be in red or should be in blue, right? These should be in red and these should be in blue. Some can also be quite ambiguous. Like for example, this current classifier is going to make an error in this top triangle. Right? It's kind of right in the middle, but it's going to make an error on this triangle. So in pseudo labeling, we saw they're going to take the current classifier that you have and label this few points based on this current classifier, but only going to label the ones which we're most confident in. So most confident meaning the ones furthest away from decision boundary. Right, so these two are going to be labeled as red because they're on one side of a classifier, and these two are going to be labeled as blue because they're on the other side of a classifier. Right? So that's pseudo labeling. So after pseudo labeling, I'm going to add these to my labeled data sets, these new 2 red points and 2 blue points. And I'm going to retrain my classifier, right? Because there's a bunch of blue points here and there's a bunch of red points here. My classifier might now shift. Right? It might shift to again something in the middle that is kind of equidistant, max margin from the red points and blue points. And then you can start seeing that this new classifier is better able to classify these two previously ambiguous points, right? With the help of my pseudo labels. So the next time you do pseudo labels again, you're actually going to be able to classify that as red correctly and this triangle as blue correctly. So of course, this is like a kind of contrived, a quick visual example. But there's some key takeaways. First, simple key takeaway. You can't label all unlabeled data points in one step, right? If I had a classifier, I train on labeled data, I immediately start labeling all the remaining examples. And I retrain my classifier, and the classifier won't change, right? So you can't do it all in one step. So the sequence in which you pseudo label is actually very important in self-training, and subsequently you're going to see in code training. The sequence is super important. And you basically find a lot of heuristics to kind of how do you pseudo label? How do you choose which ones to label first? Retrain your classifier and then label again and retrain your classifier. But it's important because you want to gradually shift the decision boundary slowly so that it covers. It actually learns a good classifier to separate all the points. Right. So the sequence is actually super important. And another super important thing is that input consistency regularization. A big implicit assumption in these methods is that the shape of my data space is important. So similar data points that I have in my space are actually going to be labeled similarly. Right? You can actually see this in practice, right? We're essentially propagating our labels based on my current classifier to the points that are nearby. So there has to be some consistency in how my points are connected and how the labels of them are also similar. That's it. All right, that's why you can also think if your data is not really separable in your dimension, it's like all over the place. You combine deep learning feature extractors to go from this unseparable to a separable space together with co-training algorithms like this or self-training algorithms. So one recent application of self-training really did it at a large scale, right? They found you can use self-training in a single view to improve ImageNet. If you have a labeled set of examples in ImageNet, you can first train a classifier. And let's just say you have a bunch of also unlabeled images. So you're going to iteratively take the initial classifier that you have, label some of these unlabeled images, while also doing several things. Data augmentation to get more unlabeled images, drop out your model and stochastic depth on your model. But those aren't super important. The biggest important thing is then, how do you actually get input consistency, right? We basically wanted this assumption that you have data points similar in space, that you could propagate your labels, and also these have to be close enough in a pattern so that you're shifting your classifier gradually whenever you relabel and retrain your classifier. Essentially, two big themes have emerged, and these perhaps should not be surprising. One is data augmentation, and one is adding noise, right? If you don't have these 2 points, right, or these 2 points, you can't really shift your classifier gradually to classify these correctly. So you need to have these points to fill in the space. And these points should be the ones that you're confident about. So similar to the existing points that you have already labeled, and also points that are similar in labels. Right? So a good way of doing that is to gradually augment your data. Because if you augment your data, you know that the labels should stay the same. And you can also control how similar they are in your data space. Data augmentation and adding noise. This theme of adding noise is super interesting, right? We saw adding noise in diffusion models. And now we also see it here. Adding noise, while it seems like a bad thing, is actually a cool way of shifting your data, kind of data augmentation, right? Controlling the changes in your data while maintaining the fact that they should have the same labels. All right, so any question about self-training and how these tricks of self-training? Yes? Exactly, so that was point 2. The sequence of labeling is very important. You can't just label everything in the beginning. You also, as you saw in this simple example, you want to label the ones that you're confident with, so that you're gradually shifting the boundaries. So notions of confidence, uncertainty, there's a bunch of heuristics over there. Yeah. At some point, I think at some slide, I had a reference for like a survey paper on self-training. But if not, it's just self-training, a survey. That's the name of a survey paper. So it goes into all of these. Okay. So that was self-training, the single view version. So now back to co-training. So you call co-training had just two views, right? You're going to have labeled data, you're going to have unlabeled data from both views. You're going to use the classifier to train F1 on the first view and F2 on the second view. And the key idea is they're going to use F1 to label more data that's unlabeled, just like self-training. But at the same time, you're also going to use F2 to label new unlabeled data. So you're going to do this self-training version twice. And once you're done, you're going to retrain your classifiers F1 and F2 until there's no more label samples. So let's actually see co-training in practice. As we motivated, the initial setting was that X1 was text on the web page, X2 was text on the hyperlinks coming into the web page, right? And Y is just trying to predict what category the web pages are: academic, sports, news, or music. Yes. Let me go through this example, right? Then I think it's going to be a bit more clear. So just see in practice. So this is LP's website, and X1 is just a text on LP's website. X2 is going to be a text on hyperlinks that point into LP's website. So that's my website. I point to LP's website because I say LP is my advisor. So that's X1 and X2, right? We're going to assume that we have labels. So in this case, Y is just LP's website is academic. So let's label data. So I can start by training classifiers F1 and F2. Right? F1, I can learn that based on a text on the website, perhaps the fact that CMU, LP's website contains the text CMU, that's going to be academic. Okay? And for X2, those are the text on the hyperlinks that point into LP's website. So for my LP's website, where I actually reference LP, I use the words advised by. So now I learn the F2 classifier, the words advised by, is something academic. Okay? So now let's say you go to my website. My website is unlabeled. Right? You didn't have time to collect data points on my website. So that's going to be unlabeled. So how can I actually label this? Well, I don't have any hyperlinks that point to my website that say advised by, because I don't advise anybody. I have, however, the word CMU on my website. So that's F1, right? So it satisfies F1. I can use that as a label using F1 CMU equals academic to label my website as being academic. Then I can start training a classifier X2, right? Based on the text that on the hyperlinks that point into my website. So there's not many hyperlinks that point to my website. LP is one of them because LP lists me as a student in the PhD program. So you can learn that a subsequent website that points into my referencing PhD program should classify as academic. So you can start seeing how this works, right? You have F1 that you can use to label this data, but F2 is not useful to learning this data, not yet. But once you have the labels, you can train F2, right? Now you're expanding the set of F2s that also lists that if someone talks about a PhD program, points into your website, then your website is academic. Right. And let's just say we have another student, also is unlabeled. And let's just say this student is somewhere else, maybe at Berkeley, for example. So Berkeley, on the student's website isn't something that you already have in F1 because we've only classified the CMU as academic. But however, this other student has some reference of PhD programs from their hyperlinks. So that's F2. So using F2, you can label the fact that this student's website is academic, and then you can expand your hypothesis of F1, knowing that this student, who's perhaps a grad student at Berkeley, should also be labeled as academic. Right. So after all this, you're learning a bunch of things, right? You've learned 2 steps of F1, CMU and Berkeley academic. That's just text on a web page. And you've also learned a couple of things about F2, the fact that if someone's website points to you and say that you're advised by them, that's academic. If someone else's website points at you and say that you're in a PhD program, that's academic. Yes. But that's why the assumptions for this working, and also the fact that self-training, which is a single view version working, there has to be some assumptions, right? If you start by, if your first step immediately captures spurious correlation, and you're just reinforcing that spurious correlation forwards across all iterations, that's not going to be really good. So you got to find the sequence, the right sequence of labeling your data points and also retraining your classifiers. Okay, so just to reiterate some of the assumptions. Again, there was this big assumption of multi-view redundancy. But essentially what we saw is that, first of all, either view is sufficient to predict the label, right? You should be able to, on a new web page, if one of the classifiers isn't confident, you should be able to use the other one to predict it. Right? So either one alone should be useful to predict the label. But in practice, of course, this isn't true. And also in practice, that's where like code training and these algorithms shine, because you don't have that many label data. So theoretically, it's able to predict a label alone if you had all the data, but you don't have that much data, right? So you're going to start with very little label data. You can't predict the label, but with all the unlabeled data, you're going to eventually be able to predict the label. That was one big assumption. The other big assumption, as we saw, is that your view should be as independent as possible, right? Given the label. And we saw this in practice, right? If you went to my website is mention of CMU. So that allowed me to predict the label. So F1 was good on my website, but F2 was rubbish, right? F2 knew nothing about my website. So it's only under that setting where the information from F1 to label my website actually could learn a better classifier for F2 subsequently. If your F1 and F2s are correlated, right, both already give good predictions with high confidence on my website, then this wouldn't really happen. Right, so you want examples where your first view is high confidence, but not the other one, and vice versa. So visually, just that also helps. Let's say I have first view, that's triangles, red and blue. I learn a classifier for triangles over there. And also have second view data. I also have data for my second view, let's say those are circles, red and blue circles. I'm going to learn a classifier for my circles, right? Those are F1 and F2. And you really start seeing that right now, F1 and F2 disagree, right? They don't actually uniquely capture the separation between the red points and the blue points across both views, right? For example, it's failing on this red triangle. And let's just say that I'm going to use these current F1 and F2 to pseudo-label a new set of points that come in, right? I have a bunch of red and blue circles that come in, just circles that come in because there's no labels, and a bunch of triangles that come in. So how does pseudo-labeling work? I'm going to first use my triangle classifier to label that for circles, right? It's the intersection that's important. The same view is just like self-training. So right now, it's intersection is important. So I'm going to use my triangle label to separate my circles. Based on my triangle classifier, left is going to be red, right is going to be blue. And then I'm also going to use my circle classifier to classify my triangles, unlabeled triangles. Right? In this case, both of them on the same side. So they're both going to be blue. Right? So this cross-labeling of each other view's data points, that's important. And now, given this new set of points, I'm going to retrain it. We can first, so that's a new set of expanded data points, what we had originally, and the ones that were newly labeled. If I retrain my triangle classifier, you can see that it's shifted. Right? It's going to take into account the ones that were newly labeled as blue, and now that's shifted. And if I start retraining my circle classifier, you're going to so again see that it's going to be shifted. Right? You're going to try to classify the red and blue ones. So you can slowly see that while both of these functions, classifiers, disagree and point in different directions, after pseudo-labeling each other, they're going to slowly start pointing in the same directions until both classifiers agree and are able to both separate all the red points from both views and the blue points in both views. Right. So again, the intuitions. Either view is sufficient to break the label. Both views should be as independent as possible so that you have information from one being transferred to the other and vice versa. And also just to quickly revisit, we saw this notion of inconsistency being super important in self-training with a single view, right? You want nearby data points. You want to be able to traverse nearby data points in data space and them to have the same label so that you can slowly start shifting your classifier. Over here, we saw that in co-training, you also want input consistency. It's just that your data from some other view helps us to supplement your data space. Right? The nearby points doesn't have to be in the same modality, or it can be from a different view or different modality. But for that to happen, we need to have agreement, right? We want that both modalities should actually agree on the final label, right? If you have a similar data point from a different modality, but they have a different label, then this wouldn't hold. Right? So you want both views to agree, and therefore input consistency is achieved, which enables you to pseudo-label across your views. Right? And you can actually show that under these assumptions, eventually you're going to converge on two classifiers that both separate your data and also both agree with each other. Even though you start off with like initial classifiers that were rubbish, right? That were not very good, trained on very little amounts of label data. Cool. So those are like the basics of code training. And there's some recent applications which shouldn't be surprising. You combine code training with all your deep networks, with contrastive learning and so on. So these folks basically show that if you want to classify a video using your two views, you have RGB information from the video. You also have optical flow from the video. You can actually do code training, right? So you're basically doing this in this self-supervised learning setting where you want to do contrastive learning between your positive examples and negative examples. And the biggest hypothesis here is that the positive examples discovered by one view, for example, RGB, the positive examples that are very hard to discover in one view, for example, RGB, can be easily found in this other view on like flow. Right? And that's because, for example, RGB is sensitive to your background. So even though the person in RGB is doing the same action, it should be a positive example. These two videos can be very different because of their background, right? And so over here, both of these people are playing golf. The action should be the same. They should be positive samples, but one's indoors and one's outdoors. So you can't really learn the fact. They can actually be quite different in benefits. That's what they're showing on RGB. But optical flow, which is something that just affects motion and doesn't really, it's not sensitive to the static background. Those are going to be quite similar. They're both playing golf. So they're going to be very similar in your space. So that's an example where they have this kind of course they agree, right? That's the first assumption. They have to agree on predicting a label. That from both RGB flow, the person is playing golf. They agree. The second assumption is that they should be as independent and different as possible, right? So whatever information is provided in RGB is different in flow and vice versa. So in this case, both of them are satisfied because in flow, it's very easy to know that they're positive samples. They're similar to each other. And in RGB, it's actually not easy to distinguish that they're positive samples because they're actually quite different from each other. So therefore, you can use co-training, right? You can basically bootstrap your RGB contrastive learning classifier with your flow contrastive learning classifier by pseudo-labeling each other, pseudo-labeling the positive examples for each other. Another one I'm not going to get into a lot of detail, but it applies for language models. So over here, normally if you have a language model, you're going to put in some prompt, and you're going to rely on the language model to give you some output, right? But the biggest issue is that it's hard to get a lot of labeled prompts with the correct answers. If you have a lot of labeled examples, just find your language model, you're good. But you care about a case where you don't have that many labeled examples, right? So you can also use unlabeled examples, right? Unlabeled examples mean just with a prompt. For example, the premise, the question, hypothesis, just a prompt without the actual yes no answer. Right, so we have a bunch of unlabeled examples. One of the classifiers that you can use on the view of unlabeled examples is, for example, there's like a language model or like a BERT embedding model. And for the labeled examples, you can put that into GPT-3 and get your fine-tuned GPT-3 with those labeled examples. But essentially, these folks shown that you can use these two views. One is a GPT-3 output, that's one view. And the other one is the BERT output on unlabeled examples. That's the other view. And you can use them to bootstrap each other and get a better classifier. So another set of work that let's go very quickly talk about it. They also emerged in a similar time was co-regularization. So we saw a lot about this agreement assumption, right? The fact that both views should agree with each other, and that forms the basis of co-training, right? If both views agree with each other, you can use the classifier learner one to label the other, and vice versa. So you can also actually more explicitly enforce this, right? You can basically add a loss term on top of whatever your classification loss is. Just have a loss term that whatever you predict from F1 should be similar to whatever you predict from F2, right? You want to make sure both model predictions are similar. And then you can start in a simple case showing some theory like these folks did. But in a more practical case, this actually goes back into representation coordination. All that works in enforcing that both models that you have are similar in output space. But again, big assumption, right? A lot of the works that we saw, at least for co-training, assume that both modalities intersect and the label is fully in the intersection. So a lot of open questions, how do you relax this assumption? So taking care of the case where the labels are both in the intersecting space and also could be in the individual spaces. That's an open question. And as the student already mentioned, how do you actually quantify that? How do you actually quantify how much is intersecting and where the label is on real world data? That's a big open question. Yes. So I think in that paper, they showed that the example was flow helping RGB, and there are subsequent examples of RGB helping flow. So it's kind of symmetric, but I think it's I think it'd be a good open research question to see whether you can quantify which direction helps more, and then subsequently design like a co-training similar method, which is not symmetric. I don't think I've seen works like that. But yeah, it's a great point. Okay, so to summarize, we saw transference. Transference is all about using more data in some other modality, perhaps through pre-trained models, perhaps through a more independent view to help your prediction on a modality that you care about. So we saw transfer using pre-trained models. In pre-trained models, how you better control them, how you better condition them on this other modality that you care about. We saw co-learning, where instead of using pre-trained models, you're using the data. Right? You can add additional data at the input space, like word embeddings helping image classification, or you can also try to predict additional data at the output space, right? And finally, we saw model induction. If you don't want to combine your representations, you don't want to train a single model, you can still keep your models separate in the case of co-training and coordinate them either through relabeling each other's examples or coordinating them. So all the work in representation coordination has also a link to model induction. So there's many more dimensions of transfer, right? Just to point out some keywords, all the work in, for example, multimodal, multitask, transfer, few-shot, meta-learning falls into this. Again, search up these works, but you want to remember, like when you read these works, you want to look at what is especially multimodal about them. Right? Is it a direct extension of, for example, transfer learning to multimodal space, or actually dealing with multimodal data or multimodal methods in some way? A lot of work in domain adaptation, domain shift, label shift also falls into this. So you want to look up similar works, for example, self-training for domain adaptation, self-training for domain shift, that's also relevant. But as I mentioned, so remember, the core is still what is unique about representation learning of multimodal data, or alignment or reasoning about multimodal data that you can link with these other dimensions of learning. Right? So there's a lot of open research questions here. And finally, just to reiterate some of the open questions, a lot of the work where data is truly low resource is still hard to tackle, especially in a different modality and low resource. Settings where state-of-the-art unimodal encoders are not deep learning, that's really hard to do transfer, multitask, pre-training on. You have all these big multitask and transfer models. Can you actually evaluate how much reasoning and how robust they actually are? How can we improve that, right? We know that they work reasonably well for standard settings, but people also find that they are actually very sensitive to difficult reasoning or more robust adversarial attacks. We saw a lot of assumptions that co-training, self-training, all these works, co-learning, they all work if the data actually has redundancy, right? The fact that they overlap and the label is exactly capturing the overlap. How do you relax these assumptions? Or how do you check these assumptions in real data? And finally, next week, we're going to wrap up and talk about quantification, which aims to, at some level, interpret how much heterogeneity and how much redundancy there is in multimodal data. Cool. Thanks, everyone. I'm here for any other questions.